Hello and welcome to our presentation. Today we'll be talking about our work on implementation of a reconfigurable synchrophasor synchronization gateway and controller architecture for DERs. Of course, it is targeted for microgrids. And this work was done in the ALSET lab of Rensselaer Polytechnic Institute, and it was done in collaboration with Dominion Energy. I am Prottay. I am the lead author of this paper and I will be presenting this. So in order to talking about DERs, we first need to define microgrid. Now on screen we have the official definition of microgrid, which is essentially a group of interconnected loads and DERs with well-defined electrical boundaries forming a local electric power system at distribution voltage level, and they can operate in two modes, in grid connected mode or in islanded modes. Now of course it's a complicated system and it will feature applications like DERs, wide area monitoring system, wide area monitoring, protection and control systems. And because we need this many complicated algorithms and this many complicated applications in this framework, we would typically need various hardware such as substation PDCs, aggregated PDCs, local PMUs of course, network extension and controller hardware. So the overall implementation is expensive. So what we are essentially doing in this paper is we are proposing a centralized synchronization hardware to replace the aggregation PDCs and some of the control and decision making hardware. And all of these are compiled into a single piece of hardware. So hopefully we are reducing some cost there. With that background, let's look at the state-of-the-art control and instrumentation architecture in a microgrid. We can see that we have controller, we have substation level intermediate PDCs, we have top level aggregation PDCs, and we have all the local PMUs. All of these are in accordance with this microgrid model, which has batteries, PVs, diesel generators, and utilities. All of them are sharing a load. From the get-go, we can see that there's a long loop and a lot of latency in the control system. And of course, there's a lot of hardware. So can this be simplified? To answer this question, this is our solution. We are putting our SSGC hardware, which is replacing the aggregated PDC and which is featuring some of the control actions on top of it, so that the local controller gets a lower share of the computational job. So hopefully the implementation is faster and clearly the latency is reduced. So this is our hardware, this is the infrastructure we are proposing. And what are the exact contributions in this paper regarding this architecture? So to begin with, we are proposing this alternate architecture. We are implementing a control system in this architecture, and then we are testing the robustness of that control system that is under SSGC architecture, Synchrophasor Synchronization Gateway and Controller architecture, under varying communication network conditions with multiple PMU streams. And for this implementation, we tested up to 3 PMU streams. So with this background, let's go ahead and look into what we have tested and implemented. So before we deep dive into the control system or into the experimentation, let's review the system we had under operation. We had a microgrid system which had diesel generator, PV system, battery inverter. We had passive load that combines fixed and interruptible loads. And in order to do experimentation, we had the provision of applying step changes to the loads. On the control system front, the primary control runs inside the Typhoon HIL-604, which hosts the entirety of this microgrid. The microgrid we just spoke about is hosted on a Typhoon HIL-604 real-time simulator. Most of the secondary control runs in our hardware, which is the Synchrophasor Synchronization gateway and controller hardware. And of course, the control system will feature a lot of instrumentation and networking hardware, which will connect the Typhoon HIL and the SSGC. Now, for further clarification, we must mention that the SSGC, which we are mentioning multiple times, it was implemented on a National Instrument Compact Trio hardware platform because it provides good options for configurability and programmability. Now, we just spoke about what is inside the system, what the softwares are. Now, in this slide, we're talking about the hardware. So, as we mentioned, in order to test our system, we have to have PMUs. We have to have local PMUs connected to each of the TERs. So, we had synchrophasor measurement from PMUs, from battery energy storage system and the load. We had PMUs, which were essentially implemented on National Instrument Compact Trio devices. And the Typhoon HIL-604 produces low voltage real-time outputs of the monitored signals, which were connected to the individual PMUs. Now the PMUs are configured to take both current and voltage inputs, but our real-time simulator can only produce voltage inputs. That's why we needed a V2C conversion, or needed a barrier circuit for V2C conversion. And on the other end of our hardware, we have the network SSGC, the Synchrophasor Synchronization gateway and controller. As you can see over here, it's remotely located. It receives the V and I phasors from the individual local PMUs, and then it computes P and Q in real time. And then it operates on a simple PI control system based on those P and Q measurements, P and Q computations, and it produces the control signal, which is then immediately sent back to the Typhoon HIL-604 through an output module of the SSGC. So on the top figure, we have the actual hardware running the microgrid and some of the local PMUs. And on the bottom, we have the remote SSGC, which is reading from those local PMU measurements. So we have an idea of how the hardware looked and what softwares there were. Of course, in this slide, we are just showing the different components of the hardware just to give a better overview. Now, in this slide, we are essentially summarizing the entire system under test. We have the entire microgrid model implemented inside the Typhoon HIL-604, which is talking to some of the local PMUs, which is connected to the load, connected to the battery, and those PMUs are connected back to the SSGC, the Synchrophasor Synchronization gateway and controller, which is hosted on a National Instrument Compact Trio, which the internal graphical program is shown over here on the bottom. And you can see we have outlined the software models in green and the hardware connections in blue. And this is essentially the entirety of our experiment. Now, what experiments are we doing? We are essentially putting a interruption in the load. We are putting a step increase on the load. So once we apply the load, we are expecting the battery to respond to that load change, and we expect it to adjust its set point so that it increases its power output. So if you can see, the interruptible load is changed from 0 to 300 kilowatt. There is some internal change in the set point of the second graph. And on the bottommost graph, you can see that the battery power output goes from 100 kilowatts to 400 kilowatts, essentially covering for the 300 kilowatt load increase. So our system works. It can run a control system in a network architecture. Now, how does it actually work? So in this slide, we are showing the experimentation. So we can see that in the load injection, we are injecting 300 kilowatts of load, and once we inject the load, we are seeing the power increase. So that's what this video is showing. 300 kilowatt is being injected on Typhoon HIL. Right then, once we set that, we are seeing the increase on the controller side of the battery power output. Now, the next part of our work is stress testing our architecture. So in order to do that, we introduced a new hardware called Candelatech CT910. That hardware sits in between the PMU and the remaining network and introduces delays or introduces data drop. And under that stressed situation, we want to see how our control system works. On the bottom right, we can see that we are simply injecting 100 millisecond delay within the network. We are measuring that delay. So how does our system hold up, our architecture hold up when we introduce these impurities in the network? So before we go forward, we are just showing here how we are injecting delays. On the right hand side, you can see that we are injecting a delay of say 200 millisecond, and on the left hand side, you can see the real-time delay computation going up in a 200 millisecond step. So it's injected right here, and we have the increasing delay. So this is how the instrumentation works, but how the control works. So this slide essentially summarizes the robustness of our control system, of our architecture. So you can see we implement the SSGC driven control system and we put it to working. And then we corrupt the network connecting the SSGC to the simulator by injecting a delay which is between 0 millisecond to 500 millisecond and introducing a data drop which is between 0% to 5%. Interestingly, we can see under 0% data drop and 0 millisecond delay, the controller output is perfect. There's very high resolution. The control signal seems to be going very accurately over a 20 seconds window. And on the x-axis, we are increasing the data drop, and you can see when we increase the data drop, at 5% of data drop, the resolution is somewhat lost. And on the y-axis, we are introducing delay. And you can see, even if we keep the data drop at 0%, introducing 500 milliseconds of delays, corrupts the resolution a lot. But it's still, the controller output still holds on. The outputs are still on the manageable range. And when we put a 500 millisecond delay and the data drop is 5%, the system is barely hanging on for 20 seconds. So clearly it's working on a short window, but the resolution is being lost. But what if we don't have a short window? What if the windows are longer? So we ran 30 minute windows, or 10-minute windows of each of these test cases, and we saw how they performed, whether or not the simulation is holding up, whether or not the controller is stopping to respond. So for each test case, for each value of data drop rate and each value of delay, we are running a 10-minute window of simulation for 10 times. So for 0% data drop and 0 millisecond delay, 10 times out of 10 times, our system sustained itself. For a 10% data drop and 0 millisecond delay, only 3 times out of 10, our controller architecture sustained itself. But when the data drop is 10% and the delay is say 500 millisecond or 750 millisecond, our system is not being able to sustain itself. So the corner case is somewhere around 5% data drop at 100 millisecond or 6 or 2% data drop at 200 milliseconds, somewhere around there. There are the corner cases where there are some chances our system will sustain itself. There are chances that it will not. And it is also interesting to see that below 100 millisecond and below 1% data drop, our system is quite robust and reliable, even if we run it for a longer time. So, what are the takeaways from this presentation? So, first thing, it is possible to reduce hardware requirements by incorporating portions of the control algorithm inside our proposed Synchrophasor gateway. The compactor platform which we used for our implementation, even though it's easy and convenient to prototype on this platform, it is expensive and it needs to be migrated to a different platform. For lower delays and lower data drop rates, our architecture is very reliable. And in terms of hardware experimentation, we need to do more PMUs. We need to do lower cost implementations. Instead of using PQ, we can use the angle differences as the control signal. And in this paper, we only showed battery. We need to show control of other DERs, such as the PV, in order to get a more holistic picture. So with that, I'll conclude my presentation and thank you for listening. And if you have any questions, you can ask.